Here's our final chapter, cosmology. So this is the study of the entire universe. All right, so let's get started. So it's the structure, the evolution of the entire universe. It tries to answer questions like how big is the universe, how old is it, does it have an overall shape, how did it form, what's going to happen in the future. So these are all questions that we attempt to answer through cosmology. Now, one of the things actually that we do know pretty well now is the age of the universe, and we'll get into the story of the Big Bang, and what evidence we have that shows that is really the situation. All right, so we know that the universe is expanding. That is, space itself is getting larger. We learned this, of course, in Chapter 17 when we started studying galaxies. But it turns out that there's a very low-level background radiation, a low-level energy that permeates everything. It's in every single direction. And we're going to talk about the discussion, or we're going to discuss the first folks that discovered that back in the 1960s. So the discovery of that cosmic background radiation, as it's now called, tells us actually that the universe is roughly. It's actually, this is an older PowerPoint presentation. It's we feel that it's or the evidence shows that it's closer to 13.8 billion years old. So that is the point where the Big Bang started. So the universe began as a hot, dense, violent outburst, and there was nothing before that. I mean, there's nothing, at least if there was stuff, we don't have any evidence of it. We know that when the universe came into existence, matter and energy were being created. Space itself was being created. Space and time were being created. All right, so so as early as the 20th centuries, astronomers, including Albert Einstein, I might add, thought that the universe was infinitely old. That if you looked any direction, the local view of the where the galaxies were distributed would be slightly different from location to location, but overall, they felt that the universe was infinitely old and had no beginning and certainly would have no end. So in the 1920s, of course, starting with Hubble, Edwin Hubble, we began to realize that the universe was filled with other galaxies, not just the Milky Way, and that they were millions, and then later on we figured out that some of them were even billions of light years away. And of course that the universe is expanding. So no matter which way you look, which the zones of avoidance are just gas and dust in the plane of the galaxy where we can't see, in the visible part of the spectrum. I mean, we can see stuff in other wavelengths like infrared and so forth. But galaxies are not spread out smoothly, as we talked about in the last. In the chapter 17, we noticed that galaxies tend to exist not very few are just isolated by themselves. They generally exist in clusters, or small groups, and even and clusters, and then even the clusters form superclusters. So there's a clumpiness, if you will, to what we see in the universe today. And we think that the universe started off in a very uniform manner. That is, any matter that was created in all directions. And why did it clump in certain places and not others? Of course, that's actually still a question that we're still trying to figure out. So here's a good way of thinking about the expansion of the universe. If you imagine, like this picture here, the bubbles, a balloon being blown up. I mean, you can have buttons glued onto the surface, or some people usually one of the things I like to do in class is you'll get a balloon and you just put just get a magic marker and put little dots all over it, and the little dots represent galaxies. And then as you blow up the balloon, the galaxies are moving further and further apart, as is shown in this picture down here. And notice, it has nothing to do with the motion of any one galaxy. I mean, galaxies are moving independently of the universe expanding. And so, the thing that we measure when we get really, really far away is the red shifts that we measured are from the expansion of space itself, the balloon, if you will, blowing up. Whereas, where the balloon is four-dimensional space-time, right? 3 dimensions of space, 1 dimension of time, and it is expanding, as time goes on. All right, so now how do we know the age of the universe, right? This is an older. I think I mentioned this before. These slides are a little bit older. The accepted Hubble constant now is about 72 kilometers per second per megaparsec. But it turns out that if you take the reciprocal of the Hubble constant, and people noticed this pretty early on after the Hubble constant was discovered, that you can, and I'll show you an example of this in the hints. You get units of time. And of course, notice the units, because megaparsecs are units of distance, kilometers are units of distance, and so if you convert megaparsecs into kilometers, and you could cancel the kilometers, and you'd end up with 1 over seconds, and then 1 over seconds, and then so the seconds would go up to the numerator. So 1 over the Hubble constant would be the age of the universe in seconds. And then, of course, you can convert that into years, and it turns out that the universe is close to 4 billion years old. It's about 13.8 billion years old. That's a more modern value, more accurate value now that we know. And see, the thing is, some people talk about, like, for example, the universe is expanding. It's expanding from a single point, and so does that point represent the expansion of the universe? Well, it turns out that it's not expanding from a single point. It's expanding everywhere equally. So, for example, if you look at this picture, this is kind of showing this. Like, so if you look out to other galaxies, some neighboring galaxies, they will tend to be moving away from us, and they're moving away from us in a very linear fashion. That is, if you double the distance, you double the speed. Right? Triple the distance, you triple the speed, and so forth. But that's not unique to the Milky Way galaxy. It doesn't matter what galaxy you're on, because space itself is expanding. This bug-looking thing on an alien galaxy would look out and measure the same thing. Neighboring galaxies would be traveling at a certain speed, and then galaxies twice as far away would be traveling at twice the speed, and then 3 times the speed. Right? There's twice the speed. There's 3 times the speed, and so forth. Right? So everyone would see this same particular thing. By the way, the fact that everyone would see the expansion of the universe the same is sometimes called the cosmological principle. So, and that turns out to be an important guide into our understanding of the universe. This Obler paradox is not that interesting. I'll mention what it is. It really only tangentially reflects what cosmology is all about. Obler made this observation, as it says back here in 1823, and he said, well, look, if the universe is infinite and there's an infinite number of stars, And he didn't, they didn't really distinguish between stars and galaxies back then. But if there's an infinite number of stars, then Obler asked a simple question: why is the sky dark? Because there's an infinite amount of light that's always hitting the Earth. If there's an infinite number of stars, what makes the nighttime dark? And so that's became known as Obler's paradox. It's not really a paradox. We understand that quite well now. The universe is not infinite, so that assumption is already out the window. And of course, there's gas and dust that absorbs light, and we enjoy a nice dark skies. And of course, it's dark in the visible part of the spectrum, right? There's microwave radiation that's always coming to us even at nighttime, and radio waves and things like that. So Obler's paradox just says basically that one of the assumptions, as I said, it was that the universe is infinite. We don't think that that's true. However, we exist in our own, where we are. There is what's called a cosmic horizon. So let me see if I can explain this for just a moment. Okay. So let's take, for example, we'll just use 14 billion years just because it's an easy number and it's easy to double. All right. So if this is the Milky Way, all right. So we're not the center of the universe. It's the center of our visible universe. Okay. So that is, we can see galaxies as far as the edge. That is, as far as, it's not an edge. I shouldn't say it that way. As far as we can, as light has been, light has been traveling since the beginning of the universe, which is 13.8 billion years ago. Let's assume, for the sake of argument, it's 14 billion years ago. So light from galaxies in this direction has just had enough time to reach us. And the same thing is true for galaxies on this side, right? So galaxies over here have had 14 billion years to reach us as well. But now the thing is that if you think about that for a second, the galaxies on this side to the left cannot see galaxies over here that we can see on the right, right? Because for us to see these galaxies on the right, it took 14 billion years for that light to reach us, but there hasn't been enough time for the light to reach these galaxies over here. And vice versa, right? These galaxies over here, the light has just barely had time to reach the Milky Way, but not had time to reach these other galaxies, right? It would take another 14 billion years for the galaxies over here on the left to know about the galaxies on the right. But they certainly exist, right? I mean, we can see both. So, so that's called the cosmic horizon. So we know that there's got to be galaxies out here further than we can see. The limit is just the age of the universe, right? So, all right. So that's what's called the cosmic horizon, the maximum distance that and it's in any direction. Like, you pick a direction, you can go out roughly 14 billion years in any direction, and you'll still see galaxies. Now, they're very young galaxies, mind you, but we still see galaxies. All right, so there is more to the universe than is the visible part of the universe. That's something that I just want everybody to understand. All right. Now, how? So the radius of the visible universe. So in any direction, you just go in any direction at all, and it's actually under 14 billion years. I know it's just a nice convenient number. It's hard to keep saying 13.8 billion years, 13.8 billion years, but anyhow, so that's the radius of the universe. All right. Actually, before I get into the cosmic background radiation, I want to talk a little bit about 1962 and a group of two astronomers that were in New Jersey. looking at microwaves. So let me. Well, I'm about to run out of time. I'll pick it up in